Okay, so here is our last video for week one, and we actually have one more quick topic from 1.3 to do, and that is accuracy and precision. We were talking about the measurements in 1.3 and significant figures. And the purpose of measurements are there are two types of ways to describe measurements with accuracy or with precision. So, precision tells us how close a series of replicate measurements are to one another. A measurement is said to be precise if it yields very similar results when repeated in the same manner. So let's look down here at these three pieces of data. So we have one, two, three, measurement one, two, and three. This measurement one, and then measurement two, and then measurement three are all plotted on this graph right here. So notice the three parts here are all very close to each other. And these three pieces of data points here are very close to each other. So both of those would be considered precise. It's basically, and a lot of times we talk about this like a bullseye, like if you are an archer or if you are shooting at a target. Being precise means you hit near the same area every time. Now, accuracy is a different term to describe a measurement, and it tells us how close a measurement is to the true value, to the true value. So a measurement is considered accurate if it yields a result that is very close to the true, or a lot of times in science, we say to the accepted value. So over here on our graph again, we see that the black dots represent the accepted value. So it goes along this line right here. Now we had in measurement one, we have these three measurements right here that were very precise. They were all very similar, but look how far away they are from the accepted value. So these were precise measurements, but they were not very accurate. Not very accurate. Okay. Here we have these three, they're kind of all over the place, so they were not precise. And then look, you only had one. Whoop, I'm so sorry. There we go. You only had one right here that was actually close to the accepted value. So this is also not accurate. So that's just bad altogether. And then this last one, you see that we have all three data measurements that are really close together, so they are precise, but they are also right here around the accepted value. So these would also be considered accurate. So they are both precise and accurate. And of course, this is what we want from a measuring device. We want it to be very consistent, meaning precise, and we also want it to be close to the accepted value, meaning accurate. So, keeping instruments close to the accepted value in the lab, we usually do something called calibration. And that is where we get the instrument ready. And this, like, say, with the balance, you would do with a known weight. And you would make sure that it is reading it correctly um, and fix it so that it would be reading correctly. And that would mean that other things that you measure on there should be accurate. But if you get, say, a balance that's measuring all over the place, it's not giving you very similar measurements each time you put the same mass on it, then you know that it's not very precise. So we want all of our measuring devices to be both accurate and precise. So that was the end of talking about all our different types of measurements. And now we're going to go to section 1.4, which is using those measurements and our units and solving problems. And what this is typically called in science and in, I guess, math, you do this as well, dimensional analysis. Dimensional analysis. Okay, one of the things that makes science problems a little different than math problems is that units are important. And I would say that units are even more important than the actual numbers. Because when you're setting up what we call dimensional analysis problems, or where you're doing conversions, if you don't have the units in the correct place in the problem, then the numbers aren't going to matter because they're going to make you wrong anyways. So we often use conversions. We're converting from one unit to another in chemistry, and we use things that are called a conversion factor. We talked a little bit about these in section 1.2, but a conversion factor is a ratio of two equivalent quantities that are expressed with different measurement units. So remember in 1.2, we said that 1 inch is equal to 2.54 centimeters. This is a known equivalent. We know this already. So we can use this to set up a conversion factor. This here represents two different conversion factors, and they both mean this. So you can use these conversion factors in any type of problem in order to cancel out or get rid of one unit and convert it to another. So all of the prefixes that you looked at in 1.2, the SI prefixes, can also be used to make conversion factors. So let's look at our chart again, our table that you have in the first video that shows us our prefixes. So, some conversion factors we can write from this, and I encourage you to practice writing some conversion factors on your own. Is let's say we are looking at a conversion factor from meter to kilometer or back. So we know that 1,000 meters equals 1 kilometer. So we can set that up as two different conversion factors. It can be 1,000 meters over 1 kilometer, or it can be written as 1 kilometer over 1,000 meters. Both of those things mean this right here and can be used in problems to help us do conversions. Another example would be, let's say down here with nanometers, okay, or nanos. So sorry, I just use meters as my common when I'm doing it. But as you can see here, they use seconds. So let's say a nanosecond or nanoseconds to seconds, we know that 1 nanosecond equals 1 times 10 to the negative 9 seconds. So basically, excuse me, one, you can see here 1, 2, 3, 4, 5, 6, 7, 8, and then the decimal would go after the 1. So 1 times 10 to the negative 9 seconds. So you can set this up again as two conversion factors, 1 nanosecond over 1 times 10 to the negative 9 second, or 1 times 10 to the negative 9 second over 1 nanosecond. So both of those are the same thing as saying this. So let's look at how to do a couple of conversions. We'll start with some simple ones and then we'll do a couple of longer examples where you might use more than one conversion factor. So again, Dimensional analysis, what this is, the basis of chemistry math, is using conversion factors to do conversions or different problems. And again, remember, units are important. So for instance, we have here 535 cubic meters, and we want to convert this to 1 cubic centimeter. Well, we know that 100 centimeters is equal to 1 meter. Okay, and so we can set up conversion factors with that. We can go 100 centimeters over 1 meter, or we can do 1 meter over 100 centimeters. Now, since we have the number 535 cubic meters, we are going to want to, if you remember back in math, if you're setting up a problem like this, if we want to get rid of the meters here, if we want to cancel it out, then we're going to have to put meters on the bottom of our, sorry about that, on the bottom of our factor. So we're going to put meters on bottom and centimeters on top. So that means we know that we want to use this one. So we're going to put 100 centimeters on top and 1 meter on bottom. Now, this one's a little bit trickier because we've got our cube in here. Well, we can fix that by just putting this in parentheses and putting a cube here. Now, in chemistry, we always encourage you to use a calculator. Is it wonderful if you can do math in your head? Of course it is. But uh, why do that when you can have a calculator in front of you? So you will be provided with simple uh, n- scientific calculators in class, but I would encourage you, if you have a graphing calculator, I would encourage you to bring it to school every week because that is, they're just, I find a lot easier to use, and I can show you some tricks on them. So if we were to type this in the calculator, we would get the answer as 5.38, no, I'm sorry, 5.35 times 10 to the 8 cubic centimeters. 5.35 times 10 to the 10 to the 8th cubic centimeters. And you can see here, we started out with 3 sig figs. Our answer here is in 3 sig figs. Okay, let's look at this next one here. The speed limit in many school zones in the United States is 20 miles per hour. What is the speed limit in kilometers per hour? And we have here our simple conversion. 1 mile equals 1,609 meters. So let's take this problem and set it up. We often write things like this in the imperial system, which is a conversion factor. This actually means 20 miles in 1 hour. So this is a conversion factor right here. So we know that we have 20 miles in 1 hour. We want to know how many kilometers we have in an hour. So we don't have the conversion directly from 1 mile to kilometers, but we do have this one that we can use here. Again, we know that if we're wanting to cancel out miles, then we're going to have to put miles down here, and we'll have to put meters up here. So we fill in our numbers here. We have 1 mile equals 1,609 meters. And notice this causes, sorry about that. This causes us to be able to cancel out our miles. But we are at meters now, and we don't want to be at meters. We want to be at kilometers. So we will have to continue on with another conversion. And here we know that, let me write it up here. We know that 1,000 meters equals 1 kilometer. So we can fill that in to our problem where we have 1,000 meters and 1 kilometer. And so here we know that our meters are canceled out. We're left with kilometer, which is what we want. Down on the bottom, we didn't cancel out our hour, which is great because that's also what we want. And now when we work a problem like this, if you want to know how to put it in your calculator, you can put it in 2 steps. And this is why I like a graphing calculator, because you can use parentheses and not have to do everything in multiple calculations. So basically, when we have a multi-step problem like this, we multiply the top and then we multiply the bottom and we divide those by each other. So if you're typing this in your calculator, I'm going to just do it up here to show you, you would type in 20 times 1,609. And I know we know not to put that anything times 1 is itself, but I'm going to go ahead and put that. Divided by, and I would use another parentheses, 1 times 1 times 1,000. And I put the ones in there just so you can tell a little better where it's coming from. And then you put that into your calculator and you should get 32.18 kilometers per hour. Now, there is a little problem with this because we see that in this problem, we only have one significant figure because that 0 at the end doesn't have a decimal behind it. So that is just a trailing 0. And so it does not count towards sig fig. So we just have one sig fig. So that means this is kind of an estimated number. It's around 20. It could be 21. It could be 19. So over here, we have to change this number to one sig fig. So if we wanted to change this to one sig fig, we could round it to a whole number, which 32 is closer to 30 than it is to 40. So we would say this is 30 kilometers per hour. Okay, let's work a few more problems here on the next slide. Here are some practice problems. Again, I suggest that you pause the video for a few minutes, try to work out these problems, and then come back and check your answers. Okay, for this first one, I'll work it up here so I can have a little bit more room. So we have 2.75 hours. And we want to convert that to seconds. So if we have 2.75 and we want to convert it to seconds, well, some of you may know how many seconds are in an hour. I do, but most of us don't just have that off the top of our head, but we do know how many minutes are in an hour. And we know that there are 60 minutes in 1 hour. So we can use that conversion factor. We have hour here, so we want to put hour on the bottom so we can cancel that out, and minutes on top. So we're going to put our 1 by hour, our 60 by minutes. That's going to cancel out our hours. And we're left with minutes, but we want to go to seconds. So we know that there are 60 seconds in 1 minute. So we can plug that into our problem where we have 60 seconds in 1 minute because we want to cancel out our minutes. That's why we wrote it in that way. And then again, we are going to do what I said before, where we are going to multiply the top and then divide by the bottom. So in your calculator, you would type in 2.75 times 60 times 60, and then that is going to be divided by 1 times 1, which is 1, which we know anything divided by 1 is itself, but I wanted to type it in so you could see where everything was coming from. And if you do that, you should get 9,900 seconds. Now we go back and we look at our significant figures and we see that we only have three in our starting, so three sig figs. Well, ooh, this is a little bit harder to change to three sig figs, isn't it? But I can do that right now. It actually has two sig figs, but I can change this to three sig figs by turning it to scientific notation. And if I were going to do that, I would take this and I would do 9.90 times 10 to the third seconds. And that would give me three significant figures. Okay, let's do the next one. The next one, we have a mass of 0.845 kilograms, and we want to convert it to micrograms. So again, we can do this in multiple steps to kind of help us because most of us don't know how many micrograms are in a kilogram. So we do know that there are 1,000 grams in 1 kilogram, and we can look back at our chart if we don't know these off the top of our head. And then there are 1 times 10 to the oh let me sorry 1 times 10 to the 6 1 times 10 to the 6 grams in 1 microgram. Now here's a little weird symbol right here. This little curvy U is the symbol that we use to represent a microgram. So I'm going to set up my problem, 845 kilograms. I want to get rid of kilograms, so I'm going to use this conversion factor first, and I'm going to put kilograms on bottom and grams on top. So I end up with 1 kilogram and 1,000 grams. Then this cancels out my kilograms, but I want to get rid of my grams and go to micrograms. So I'm going to use this one as my second one. Grams on bottom, 1 times 10 to the sixth. Micrograms on top, 1. And then I am going to multiply the top, multiply the bottom, and divide those numbers. So here I'm going to type in my calculator, 0.845 times 1,000 times 1 divided by 1 times 1 times 10 to the sixth. If you do not know how to do this in your calculator, that is fine, and I'll show you when we're in person just to be a little bit easier. So if you don't know how to type in exponents, you can just add that number of zeros and type that in instead. Again, I will show you this a little bit better when we're in person because it's just easier for me to have the calculator out in front of you and show how to type that in. And it also is dependent upon whether you have just the little $10 scientific calculator or that we provide in the classroom, or whether you have the graphing calculator. So when you type this in, you should get, if your calculator doesn't show scientific notation, you'll get a number like this, 2, 3, 4, 5, 6 micrograms. But we would rather turn this to scientific notation. Plus, we see here we only have three sig figs. And even though this number only has three sig figs, because all of these trailing numbers are not significant, it still is a very large number. And for some reason, us chemists don't like numbers like that. So we would always turn a number like this into scientific notation. And we would do this by doing 8.45 times 10 to the eighth micrograms. So because we go 1, 2, 3, 4, 5, 6, 7, 8 places. And so it is 8.45 times 10 to the 8 micrograms. All right. Our next one, oh, I am so sorry. This should have been, let's see, one. This should have been a negative here. I'm sorry. Negative. Okay. But still, you would, so instead of this, you would have typed in 0.0000001. Sorry about that. Okay. So let's look at this next one. This next one is very similar to the one that was on the other page. And it says a car travels at a speed of 65 miles per hour. Convert this speed to meters per second. And here you're given the conversion 1 kilometer equals 1.61 kilometer equals 1 mile. So 65.0 miles in 1 hour. We want to get rid of miles, and we can go to kilometers here. And we know that 1 mile is 1.61 kilometers. So this gets rid of our miles, but we still have kilometers, and we want to go to meters per second. So here we're going to get rid of our kilometers by we know that there is 1,000 meters in 1 kilometer. This gets rid of our kilometers and leaves us with meters. But look back here, we have hour, and it's asking us for second. So even though we now have meters as one of our units, we need to have meters per second. So we need to have second on the bottom. So we are going to get rid of our hours. And if we have hours on the bottom here, the way to get rid of it is to put it up here on the top. And again, we know easily our minutes, 2 hours. So we're going to say 60 minutes in 1 hour. Notice that gets rid of our hours, and now we have meters per minute, but again, we want meters per second, so we're going to keep going, and we'll put minutes here and seconds here. We have 60 seconds in 1 minute. Now, this one's a doozy to put in your calculator. You're going to do 65.0 times 1.61 times 1,000 times 1 divided by basically 60 times 60. When you do that, you should end up with the nice number, once we account for 3 sig figs, 30, oh, not 30, sorry, 29.1 meters per second. Okay, I know dimensional analysis can be a little daunting at first, and I promise you it does require some practice. If you have not done this in a while, or even if you have, it always requires practice because you can notice that sometimes, like up here, even I make little mistakes. Anytime you're doing multi-step math problems, there is an opportunity to make mistakes. So the more you practice, the better you get at it. In your textbook, your online textbook, there are lots of example problems and some practice problems in there that have the answers to them. You also have several practice problems like this in your assigned homework in Alex. So I encourage you to practice, and then the next time that we are together in person, hopefully we'll have a little bit of time for me to run through and practice some of these with you. We will have a lot to cover in the second week of lecture, but there should be a little bit of time to practice some of these problems. I hope you have a wonderful rest of the week and stay safe. So this is the last of our week 1 lecture. Have a good one.